In this lesson, we're going to be looking at the flying falcon to help us understand the instantaneous rate of change of a function. Did you know that the fastest animal in the world is the peregrine falcon? It is the fastest animal in flight, fastest bird, and the overall fastest member of the animal kingdom, even when compared to the cheetah, whose top speed is only 75 miles per hour. The peregrine falcon achieves its highest velocity not in horizontal level flight, but during its characteristic hunting stoop. While stooping, the peregrine falcon soars to a great height, then can dive steeply at speeds of over 200 miles per hour. Our application is the instantaneous rate of change of a function. Here's our problem situation. A falcon takes off from the ground at time x equals 1 second. It's going to climb for a while, then dives for a bit, then swoops back up again. The graph below shows what its height is as a function of time. From the graph, you can tell that the falcon is still climbing at x equals 2 seconds. The question, at what rate is the falcon flying at the instant x equals 2 seconds? So what's the instantaneous rate of change? We saw in a previous lesson that that's represented by the slope of a tangent line. So I'm going to go ahead and I'm going to put my straight edge right here at time equals 2 seconds. And I'm going to try and model what a tangent line to the curve looks like at this time. So this tangent line right here, if we knew what the slope of that linear function was, it would represent the slope of the graph at time equals 2 seconds. How can we find the slope of that tangent line when we only have one point? Typically in the past, when we want to find slope, we usually have to have 2 points. We call that the average rate of change if we know 2 points because we can subtract the y-coordinates and divide by the difference of the x-coordinates. A line that passes through 2 points is called a secant line, if you'll remember, but a line that passes through 1 point, like right here, is called the tangent line. And the tangent line is important to us because if we can get the slope of that tangent line, it models or tells us what the slope of the graph is at that time. So the slope of the tangent line is going to tell us, okay, what's the rate of change of this bird at that time. Well, let's remind ourselves back over here that rate equals distance divided by time. If you remember this little formula, distance equals rate times time. If you wanted to isolate the rate, you would divide both sides of this equation by time, so hence we get rate equals distance divided by time. But an instant is 0 seconds long. So in 0 seconds, the falcon would travel 0 feet. So in this thought process, the instantaneous rate takes on the indeterminate form 0 over 0. We've seen the indeterminate form before, and when we apply limits to it, sometimes we have to do some algebraic work to get the answer for that limit problem. All right, so does that mean that the falcon's instantaneous rate can't be determined? Well, from our study of limits, we know that answer is no. We just need other means to determine it. All right, let's get inside this problem then. The falcon's height is given by this cubic polynomial equation. Now, the word polynomial just encompasses that class of functions where your graph is well behaved. And when I say well behaved, I mean there's no discontinuities. So the graph is continuous. You can draw it without ever lifting your pencil. So all polynomial functions are well behaved or they're continuous functions. So the falcon's height is given by this function where x is in seconds and f of x is in feet. So we want to investigate at what rate is the falcon flying at the instant x equals 2 seconds. All right, so down here, part 1, finding the instantaneous rate of change at x equals 2 numerically. So let's investigate this question using an approximation. To find an approximation of the instantaneous rate of change, I'm going to call that IROC, instantaneous rate of change, at which the falcon is flying at x equals 2 seconds, let's just find the average rate of change over a small time interval. Now, h is going to represent the distance between two time values, and we want to make sure to include units on all our answers. All right, so for problem number 1, it says, let's find the functional value at 2. So let's find f of 2. Let's find the height of the peregrine falcon at x equals 2 seconds. Well, let's not forget about our calculator and using that to assist us. So why don't you guys go ahead and go to y equals, enter this cubic equation. Then I'm going to quit out of that. Then I'm going to hit the alpha key and trace. I've stored that cubic equation in y1, so I'll access it. I want to evaluate y1 at the time 2. So that tells me that at 2 seconds, the Peregrine Falcon is at 20 feet. Don't forget to include your units. All right, so that would be this ordered pair right here, 220. All right, so 1 second away from 2 seconds, when we get to 3 seconds, which that means h is 1 second, because h represents the distance between the two time values. Let's find out how high it is now at 3 seconds. So it's about right here. So I'm just going to go back up and grab what I had already evaluated, and now it's an editable line, so I can go in here and press 3 and record 26 feet. Now, of course, you can use your table feature too. You can also use your graph to trace if you want, so let's remind ourselves about that. Remember, we have the equation, the cubic equation stored in y1. Let's go ahead and graph it. Probably you're in the Zoom 6 window, the standard window. Well, this doesn't at all look like this graph right here. Well, of course it doesn't. Let's go ahead and use what we see here to assist us in setting an appropriate window in the calculator. Let's not struggle here setting a window when the window can already be found by using the values we have here. So it looks like in this graph that they've labeled the independent axis, which remember the independent axis, that quantity is time, the variable is x, and time is measured in seconds. And just a reminder, the dependent quantity is the height of the Peregrine Falcon. The notation for that is f of x, and the height is measured in feet. So let's go to our window. Now notice that we're interested in 0 to 7 seconds. It's okay on the independent axis if you overshoot that, so I might just go to 8. I'll count off by ones from 0 to 8. Okay, along the y-axis, I'm just going to start at 0. And it looks like these tick marks represent 5s. So it looks like this is at 20, so I might as well go up to about 40. So y-min 0, y-max 40, and it looks like they're counting by a scale of 5. So I'm just going to try and model this as best I can. Now I'm going to hit graph, and I'm going to hope that my graph looks more similar to the picture, and it does. So as a reminder, I can find the values, the functional values, by hitting trace, pressing 2, pressing enter, so we can see 220 as a point on that graph. You can just go ahead and hit 3, and we can see 326 is another point on that graph. So it's just whatever you choose to use to find the functional values. All right, so what's the average rate of change over this interval? So what we're looking at is, now if I look at 326, it's about right here. The average rate of change is going to best be looked at by finding the slope between these 2 points at x equals 2 and x equals 3. So let me connect those 2 points, which is no longer a tangent line. It's now a secant line. And the slope of that secant line represents the average rate of change in that 1 second time interval. All right, so what we want to do over here is we want to set up a difference quotient. To get the slope of that secant line, we want to set up the notation. We want to say the y value at x equals 3 minus the y value at x equals 2. Let's include units in our work. So these numbers right here are y values, or in this case, f of x values. They're measured in feet. And then the difference of the two x coordinates of these 2 points would be 3 minus 2. And this is in seconds. So find the average rate of change over this interval. All right, so I'm not going to do that work. I'm going to come over here and let the calculator do it for me. I'm going to go back to the home screen. I'm going to set up a fraction bar. And we're going to do y of 3 minus y of 2. I believe we did this in the swinging door problem, so you may have familiarity with this. I hope you do remember that. And then I can just put down 1 here, or I might as well just do 3 minus 2. But of course, I know numerically that 3 minus 2 is 1, so it won't matter. In our setup, we want to show 3 minus 2. All right, so I get an answer of 6 feet per second. Now, if I wanted to change this to miles per hour, I'd have to do some conversions That's not the point here, so we'll just continue finding our answers in feet per second. All right, so we have an estimation of the instantaneous rate of change by using an average rate of change, and I guess that's a pretty good estimate, but can we get a better estimate of the instantaneous rate of change at 2 seconds? Well, look at problem 2. Notice now that we're still interested in the functional value at x equals 2, but now notice that our new time value is closer to time equals 2. It's at 2.5. So the difference between 2 and 2.5 is our h value. And now let's figure out what is the average rate of change in that half-second time interval. So if we want to look at the graph, let's say now I come over here. Here's 2, here's 3, but 2.5 is here. At 2.5, if I go up to the graph, perhaps I'm right here. Notice this point is now moving down the curve, getting closer to the point that occurs at x equals 2. All right, so let's go ahead and draw in that secant line. Okay, and just kind of make a prediction in your brain. What do you think about the slope of this secant line? Is it a better approximation to the slope of the tangent line? Yeah, and it seems to be getting more steep because this is 6 feet per second. Now this is probably going to be greater than 6 because this secant line is steeper than this first one we found here. All right, we know f of 2 is 20 feet. So I'm going to go back to my graph and I'm going to use my graph this time. I'm going to use trace and I'm just going to do 2.5. So in that half-second time interval, the Peregrine Falcon traveled the difference of these two values a little more than 4 feet. So what's the average rate of change then? Well, that's the difference quotient, y2 minus y1 over x2 minus x1, the slope formula. So we do f of 2.5 minus f of 2 feet over 2.5 minus 2. Again, go to your calculator, home screen. I'm just going to go up here and grab this, and I'm going to edit this to 2.5. So I hit 2, but then I need to hit the insert button here. So above the delete key in blue, second insert, and I can put the 2.5 without messing everything up. Okay, well, that's the number I thought. Well, it's more than 6, which is what I thought it should be. Okay, so I think you see kind of the trend of what's happening here. Now look at example 3. What if we want to find and calculate the average rate of change between x equals 2 seconds and x equals 2.1 second? So now our h value, which is still decreasing, is 1/10 of a second. So same thing here to calculate the average rate of change over that smaller time interval. So you can even see it, I can't even graph 2.1 on here, but that point would be so close to the point at x equals 2. And if I were to draw the secant line through those, that line's going to be even a better model for the tangent line. So I'm thinking that the closer I get to time equals 2 seconds when I look at the difference between these two values, the better approximation I'm going to have for the tangent line. So go ahead and take the time to fill this in. Go ahead and stop the video and fill all that in, and then come back and check. Notice this h value is 1/100th of a second away. So that's a really close secant line to that tangent line. the number suggests that maybe I'm approaching 12 feet per second. So let's go ahead and turn it over. There is one more difference quotient to calculate on the back. Think about what the h value is here, the difference between these two times. I mean, the 0.2.001 is so close to the point at x equals 2. So the h value, the difference between the two time values, is 1/1000th. I'm going to set up the same difference quotient, and we're going to get 11.993001 feet per second. I feel like these numbers are leveling off to 12. Even if I chose the 2.0001, I don't think that this is going to jump past 12. That's my prediction. And of course, you have the difference quotient here. Okay, let's think through some of these questions then. It says, as smaller and smaller time intervals h, as h is decreasing, are found, what value is the length of the time interval approaching? Well, I saw from the trend of the numbers that h appears to be approaching 0. Remember in our limit statements when we would allow x to go to 0 or delta x to go to 0 or h to go to 0? That's what we're kind of setting up here. What value does the average rate seem to be approaching? Well, I think with the trend of the numbers, the rate seems to be approaching 12 feet per second. These have all been average rates of change because we've been finding just difference quotients like this right here. It says, simplify the expression below to find the average rate of change for the Falcon given an unknown time interval h. Show all work. Oh, remember in our first example that we did, we used f of 3. So our first h value was 1. So when h was 1, then this was calculated to be f of 3, and this was 3 down here. In our next set of problems that we did, difference quotient, h was 0.5. Because when h was 0.5, then when we summed it, added it to 2, we got 2.5. And then down here we did 2.5. So h just represents those unknown values of the time difference between x equals 2 and another x value of a point. So simplify the expression below to find the average rate of change. All right, to simplify this expression, I've got to find something to plug in for f evaluated at 2 plus h, and I've got to find something to plug in for f of 2 so that I can perform computations. I can't perform computations on notation. So I'm going to kind of come over here and go, oh yeah, I was working with the equation, that cubic. So let's write that down over here. I think it was minus 40. Yeah. So I know that f of 2 was already found to be 20 feet. Okay, so we've got something to plug in for f of 2. We've got the number 20. So what is f evaluated at 2 plus h? Well, I'm going to have to insert 2 plus h in for all of these x's, these 3 x's right here. So 2 plus h cubed minus 13 times 2 plus h squared. Oh, that goes on the outside. Where am I at? I'm going to swing it down here. Plus 52 times, not x, but 2 plus h, and then minus 40. Just needed to leave myself some room here. Okay, so now I've got this difference quotient. Remember, we haven't put a limit in front here yet. Okay, that's calculus when we do that. Right now, we're just calculating this difference quotient. Okay, so in the denominator, I'll go ahead and clean that up. If I remove the parentheses, the 2's will cancel, and I just have h down here. Where f of 2 plus h is, I'm going to replace it with its equivalent notation here. Right, then I have minus, which goes here. F of 2 is going to be replaced with this little bitty 20 here. I'll go ahead and put in equals because I'm going to move down. Okay, still got the H down here. So now we've got a lot of cleanup here. So I went ahead and cubed this. I went out off to the side and I multiplied 3 of these binomials together. And what I'm going to write down here is going to be the result of that cubing. So 8 plus 12h plus 6h squared plus h cubed. These 4 terms are what you add or subtract, came from, it was the result of cubing that binomial and cleaning it up. The next few terms I'm going to write down comes from squaring this binomial and then distributing a negative 13 through it. So the next few terms are minus 52, minus 52h, minus 13h squared. So these 3 terms came from the process of squaring that binomial and distributing a negative 13. So now I'm here, so 52 times 2 is 104, plus 52h when I distribute. And I'll just go ahead and clean this up, and this is minus 40, minus 20, so that's minus 60. All right, let's see what can cancel. So I have got a lot of things here. Let's look at the numbers. If you add 8 and 104, that's 112. But these 2 negative numbers are also 112 when added, so those will cancel to 0. I think I can collect the 12h and the 52h. Let me get the h cubed down here first. I'll kind of lightly cross it off in case I make a mistake. I can still see it. Then I see 2h squared terms, so it looks like it's minus 7h squared. And then it looks like I've got, minus 52h here and plus 52h, but that just leaves this 12h here. If we did all our work right, all terms in the 12h, sorry. If we did our work right, all terms in the numerator should have h's in them. All right, I would prefer to work, well, let's see if I can work down one more time. It's gonna get kind of crowded. In the numerator, I'm gonna take out the GCF of h, so h pulls out of h cubed, leaving h squared. H pulls out of here, leaving 7h, and h pulls out of here, leaving 12. So let me come up here. I can divide these h's out, so now I'm left with h squared minus 7h plus 12. So that's my answer. I do all that work, that's my difference quotient. This is like a little formula that will help us find the rate of change, the average rate of change, if we knew what h was. Let's just test it out. Okay, remember what our first h value was back over here? We went from 2 to 3 seconds, so our h value was 1, and when your h was 1, we got 6. Let's see when we plug in 1 for h, do we get 6 back? So that'd be 1 minus 7, which is negative 6, plus 12, which is 6. All right, let's try the next h value. Remember, in our next problem, we got closer to our point at x equals 2, and we were only a ½ second off. So if h is 0.5, then we got a rate of change of 8.75. So let's come over here, and let's just kind of verify that this is correct. So I'm going to plug in 0.5 and square it. Minus 7 times 0.5 plus 12. Yep, 8.75. So hopefully you believe that this answer right here will help you calculate the average rate of change if you know the h value, the time difference between the 2 points that you've chosen. All right, and to kind of wrap up what we've done here, what happens when we put a limit in front of this difference quotient? So as the time interval h approaches 0, the average rate of change approaches the instantaneous rate of change of the Falcon at x equals 2 seconds. So evaluate the limit showing all work. Okay, that's not a lot of space right here for me to do what I've done up here with the limit in front, so that's okay. This limit statement right here is equal to the limit as h approaches 0. Sometimes you'll see it written kind of, it depends upon the software. I like to put it down here just to kind of keep it organized. So what's the limit as h approaches 0 of this difference quotient? Well, I already did all this work. This difference quotient is equal to, I'm just going to steal it from up here, is equal to this expression right here. All right, now I'm ready to plug in 0 for all the h's I see. So this term will go to 0 and this term will go to 0. So when I plug in 0 for the h's, I can lose the limit statement, and look what I'm left with, 12. So by applying the limit statement to this difference quotient, we have just found an instantaneous rate of change. And 12 makes sense because we just figured that looking at our predictions up here that it looked like the rate of change was going to be 12. But this is the way we actually prove that it is. So 12 feet per second. This is called the instantaneous rate of change, IROC. This is the average rate of change, but when you put a limit statement in front of that, it becomes the instantaneous rate of change. All right, and one more thing I want to share with you is this right here. This big ugly limit statement right here. This limit of a difference quotient. Okay, we could say that that's equivalent to this nice compact notation. We can say that this whole thing right here is equal to the notation f, the function was f, so I'm going to use f, prime. Prime means the slope. So if you see the prime, think the slope of f at 2. And I'd put 2 in parentheses. Don't confuse that f of 2 is the y value at x equals 2 on the function. But the prime is actually the rate of change of the function at time equals 2. So if you see this notation, f prime of 2, that means we really have done a limit of a difference quotient to get the instantaneous rate of change. All right, now there's more to do in part 2, but I think I'm going to do that in the next video.